So today we're going to look at 5.3, and these are the things that we want to cover. We want to find a common log and natural log with and without calculators. We want to be able to convert from exponential to log and log to exponential. That's really important. We want to use the change of base formula to solve logarithms that we can't normally calculate, and then graph logarithmic functions. And we probably won't get to the applied problems, but we'll take a look at those in a little bit. So let's start with this. This guy here, this equation that you have, these two things are equal. This first half is in log format. This is log format. And this guy is exponential format. Exponential format. So they are the same thing. These two statements are equal to each other. It's just one is in log format, the other one's in exponential. And you have to be really well versed in going from log to exponential and exponential to log. So it's the same idea as this. Negative 5 minus negative 6 is equal to negative 5 plus 6. And you guys know that you do this like same change thing, and that makes it a positive 6. But the difference is one's written in subtraction format, the other one's written in addition format. They're the exact same problem. They're the exact same number, just different formats. The same thing's true with these two. This one is written in log format, and this one is written in exponential format. They're the same idea. They're the same number. They're the same concept, just one's in log, one's in exponential. So how do we use that? Well, let's solve these. And so for each of the following, let's figure out what these are equal to. So we'll start with this first one. And this is in log format. And again, our brain does not like log format. So let's convert it into exponential format. To do that, this will be 10 to some power equals 10,000. So what is x equal to? X equals 4. So that means this is equal to 4. So we rewrite it from log format into exponential, and then our brain can actually start to work on it and say, oh, maybe x is equal to 4. Okay? Let's do the next one. So the same idea. This is b. So we're going to say log base 10 of 0.01 equals x. Solve it for x. So when you convert it, you're going to get 10 to the x power equals 0.01. Now 0.01 is kind of a goofy number to say. Instead, I'd like to say this as 100th, which is the same as 100th. So x equals negative 2. Squaring it, the 2 gives you a 100. Taking the negative of it reciprocates it. So here, x equals negative 2. This is equal to negative 2. You have to remember that if you have a divided by b to the x power, that equals b divided by a to the negative x power. Negative exponents reciprocate. They flip numerator and denominator. They don't make your sign negative. They don't change the sign. They reciprocate the fraction. All right, let's do part C. So part C says log base 2 of 8 equals x. Solve for x. So again, this is in log format. You're going to rewrite it in exponential. So you're going to rewrite it as 2 to the x power equals 8. So x equals 3. Letter D, and I won't rewrite it. I'll just write it in exponential. 9 to the x power equals 3. 9 to what power equals 3? And from this one, you have to bring in from your brain the square root of 9 equals 3. So the square root of 9 is equal to 9 to the 1/2 power. So you have to know how to go from radical to exponential. Radical format, square root of 9, is 9 to the 1/2. So in this case, this equals 1/2. All right, E. 6 to what power equals 1? 6 to the 0 power. So this is equal to 0. And letter F, 8 to what power equals 8? 8 to the first power. And these use the idea that anything to the 0 power equals 1, and anything to the first power equals itself. It's not just converting from logs to exponents, it's also knowing the laws of exponents. You have to know the reciprocal law, this guy. You have to know anything to the first power and anything to the 0 power. And you have to know how to convert radicals into exponents. Your calculator can only handle two types of logs. Two types of logs. The first type of log is called the common log. And the common log is base 10. The natural log is something called base E. And so let's talk about base 10 log real quick first, and then we'll talk about base E. So if you see something that is just written as LOG, that means log base 10. And this is called the common log. It's probably called the common log because our entire number system is base 10. And I think we talked about this earlier, but when you look at your place values, you have the ones column, the tens column, the hundreds column, the thousands column. And the ones column is 10 to the 0. That's 1. The tens column is 10 to the first. 100 is 10 to the second. 1,000 is 10 to the third. So we are a base 10 number system. That's what we use. Probably because you have 10 digits on your hands. Right? If we encountered an alien civilization and they had 8 fingers on one hand and 8 fingers on the other, their number system would probably be a base 16 number system. If you go back to the cartoon characters being base 8, like, say, The Simpsons, they're base 8. That means their first would be 8 to the 0 power, 8 to the first power, 8 to the second power, 8 to the third power. So when they counted, they would count 1, 2, 3, 4, 5, 6, 7, so 0 to 7. And then for the number 8, they would write this. That's 8. Here's 9. Here's 10. Here's 11. Here's 12. In a base 8 system. It's a different way of counting. It's important to understand why we're a base 10 system. And this is called the common log. Okay? The other type of log that you can have is called the natural log, and this is a base E system. And we'll say natural log. And this is called ln. ln of x. And this is base E. This is equal to log base E of x. So what is this number E? E is approximately 2.7. And it's called Euler's number, or Euler's constant. It's a number just like pi. So pi is this irrational number. It never repeats. It never ends. It keeps on going forever and ever. It pops up in circles and it pops up in other places. E is a number just like pi, except for the places where you use E are a little bit more complicated than the places where you find pi. Pi is found in circles. And area of a circle, you probably learned about pi maybe when you were in, 5th, 6th grade, maybe middle school. You started doing areas of circles and circumference of circles and things like that. And all of a sudden there's this magical number called pi that pops up. This is E's claim to fame. If you were to take a graph like this, and you were to make a graph, maybe something like this. So here's a graph of a function. At every point on this function, so at x equals 1, you could take this point and you could find the slope of a line of that point. So maybe the slope like this, maybe that line has slope equal to 1/2. And then if you pick the point 2, you could pick this point and you could find the slope at that point. Maybe this is -2. And if you picked a point 3, you could find the slope at this point and it would be, -1. m equals negative 1. Okay? So this is actually the slope of this line. The slope of this tangent line is called the derivative at the point, but this is what you're going to learn about in calculus, okay? All calculus is spent learning how to do a lot of this stuff. So it's important. If you were to draw e to the x power, so if you were to make the graph of this, and this function was e to the x power, the cool thing about this is that at the point 1, the slope of that tangent line is 1. And at the point 2, the slope of that tangent line is 2. And at the point 3, the slope of the tangent line is 3. So imagine trying to explain pi to like a kindergartner. Like, hey, the area of a circle, and they're like, what's a circle? I don't know. This is kind of the same thing that's going on with e. You may not recognize e here. You might be like, oh, it's just some number, I don't really get it. You will really get e in calculus. So on your calculator, if you're asked to calculate the following common logs, so these are common logs, so that's base 10. These are all base 10. You have a button on your calculator, and it looks like this, log. That's the base 10 logarithm. It's not base 8, it's not base 2, it's base 10. So if you punch this in your calculator, and depending on your calculator, some of your calculators, you push the log button first, and then you punch in the number. In other calculators, you put the number in first, and then push the log button. Either way, you got to know how to use your technology. You plug this in, and you get 5.8. Now, there is kind of a quick rule of thumb when you're using LOG, base 10 logs, is if you count the number of decimals, 1, 2, 3, 4, 5, that is a quick approximation to what the answer is going to be. It'll get you in the ballpark. It's not going to be exact, but if you count them, because it's base 10, right? 10 to the first, 10 to the second, 10 to the third, it's base 10. So if you count the number of decimals in the number, you can see we get about 5. The same thing happens here if you take the log of this, 1, 2, 3, 4, about 5. And so you kind of get the same thing here. And this is really quick, kind of an estimation. Notice that the log of negative values does not exist. And why is that? If you think about the graph of the log looks something like this. This is your common everyday logarithm, okay? And it has an asymptote at 0. So if you tried to punch in your calculator the log of -3, which is over here, there is no graph over here. And so you'll get an error. You'll get a DNE, does not exist. If we try to do the same thing with natural logs, and here are 4 values of natural logs, the button on your calculator looks like this, ln. And what that really means is log base e. It means e to the y power equals x. And there's no quick way of estimating these. You just got to punch it in. And so this is how you do that. You take the natural log of this number and you get that. Basically, the logs of big numbers are positive numbers, and the logs of very teeny tiny small numbers are negative. The logs of negative numbers do not exist. And how about this? That is log base e of e, which means e to what power equals e? E to the first power. And then the same thing's here. True here. Log of natural log of 1 is equal to 0. Punch these in on your calculator to get some answers for these. We'll provide it if necessary on the test. But let's say you're given a problem that is not base 10 and it's not base e. How do you solve it? Using your calculator. This is called the change your base formula. And what the change your base formula allows you to do is take any log of any base and convert it into a log that you can use on your calculator, preferably log base 10. So this is the way it works. Log base b of m equals log of a, where a is the log that your calculator can do, divided by log base a of b. So m goes on top, and the base goes on the bottom. So let's try one of these. Find log base 5 of 8 using common logs. So we want to know what is log base 5 of 8. And you can't punch this in on your calculator unless you have a really fancy calculator or a change of base formula. Some calculators are coming now with change of base formula built in. But we're going to do this one by hand. So what log do we have on our calculator? We have log base 10. So let's convert this to log base 10 of 8 divided by log base 10 of 5. And no, the log base 10s don't cancel. You can't do anything like that. You have to punch this in on your calculator. So you're going to do log of 8, and I'm going to divide that by log 5. Google's so smart. 1.29. So that's the answer. 1.29. So once again, the 8 goes on top, the 5 goes down below, and the base of the log is the base that our calculator will do. You could do the same problem, find log base 5 of 8, using natural logs. So we do something like this. Log base 5 of 8 equals ln of 8 divided by ln of 5, which conceptually is log base e of 8 divided by log base e of 5. Now we don't have a log base e button. We have the ln button. So if we go back to our calculator, here's the ln button. So we'll say ln of 8 divided by ln of 5. Enter. Same number? Yeah, same, and it should be, right? It should be the same number. So this is 1.29. We're going to graph these three things, these three natural logs, and we're going to use the same ideas that we developed last week when we were graphing exponents. So we'll come back to this. So last week when we were graphing exponents, we would say, what does the everyday common exponent look like? And it looks something like this. So maybe this is like y equals 2 to the x power. That's what an exponential function looks like. Exponential growth. And there's this important part, maybe we'll call it an anchor point, 0, 1. And so then we started graphing different types of these. And so we'd say, well, what would y equals 2 to the x plus 3 look like? And this x plus 3 shifts the graph 3 units to the left. So that means you would take this anchor point and you'd shift it 1, 2, 3 units to the left, and you would draw basically kind of the same curve like this. And so that's what this looks like. And if I had x minus a number, it would shift it that number units to the right. Okay? So we talked about this a little bit. We also talked about what would happen if you took this graph and you put a number like out in front of it. Like what if I looked at the graph of y equals negative 1/2 times 2 to the x power. So what does the 1/2 do? The 1/2, if you picked every point here and you multiplied it by 1/2, it would crunch it down, right?
Yep.
Okay. So the 1/2 crunches the graph down. It squishes it vertically. It divides everything by 2. So this crunches it. We'll say divide by 2. So it crunches. What does the negative do? If this is a point of 3, if I take the opposite of it, it reflects it over here. So this negative 1/2 does two things. it crunches the graph down, that's what the 1/2 does, and then the negative flips it over the x-axis. It takes all the positives and makes them negative, takes all the negatives, makes them positive. So this graph is going to look something like this. And this is like, if this is 0, -1, it's going to go through 1/2 and then not grow quite as fast. So this is kind of a review from exponents. We can shift things up, we can shift them down. We can shift them to the left, we can shift them to the right, we can stretch them out by multiplying, or we can crunch them down by dividing. So those are the different shifts we can do. So let's use the same information and apply it here. Let's do this first one. So what does your everyday run-of-the-mill natural log function look like? It looks something like this. Here's ln of x. And it goes through the point 1, 0. And remember, just to reference like other things, here's the line y equals x, and this is the graph of e to the x. And these are inverse functions. One's the do, one's the undo. So if you have trouble graphing it, sometimes it helps to look at the inverse. So if we say the natural log of x plus 3, that means we're going to shift this thing 3 units to the left. So grab this point and move it 1, 2, 3 units to the left. And then you basically draw, if you go out 4 units, there's a vertical asymptote here. You're going to draw this graph the same way. There's no stretching, no squishing, crunching it down. You're just shifting it to the left. So this would be the natural log of x plus 3. 3 minus 1/2 ln of x. So let's do this one. What does the standard natural log look like? Something like this. What does the 1/2 do? Divides everything by 2, so it crunches it down. Okay? What does the negative do? Flips it. Makes all your positive negatives and all your negatives positive. So if we do just these two, if we apply just these two, we're going to get a graph that is flipped and crunched down. So that's a graph that's been crunched and then flipped over the axis. And now what we got to do is add 3 to this. So every point on this graph, add 3. That's what the 3 does. So it shifts it up 3 units. So the final graph will look something like this. And that's what 3 minus 1/2 ln of x looks like. Absolute value, ln of x minus 1. So again, if we kind of sketch it and come up with your common everyday natural log, it's going to look like this. Now what does x minus 1 do? Shifts it to the right. So we're going to move this 1 dot over and draw something that looks like this. So that's the graph shifted 1 unit to the right. And now what does the absolute value do? It makes everything positive. If something is already positive, does it change it?
No.
No. So all of this stuff along here stays the same. Everything that's already positive stays positive. But everything that's negative gets shifted up. So all this stuff gets shifted up. That's what the absolute value does. And so it's got kind of this weird, like it comes down like this, and then it kind of hits this kind of a goofy pointy place right there and takes off that way. So this is what the graph of the absolute value of x minus 1 looks like. Here's their solution. So the graph is a translation, y equals natural log of x, right, 1 unit, we got that. The effect of the absolute value is to reflect the negative output across the x-axis, we did that. The domain is all positive numbers greater than 1. So that means that when we shifted it 1 unit, we created a vertical asymptote, and that's the graph. So find common logarithms and natural logs with and without a calculator. Check. Did that. Convert between exponential and logs. Check. We did that. Change logarithm bases. Use the change your base formula in order to convert something from base 8 to base 10 or something like that. Graph logarithmic functions. Check.